Today's topic is current electricity. What is current? If you take any conductor and if you create a potential difference across any 2 points, let us say one is high, one is low, then what will happen? Current will flow from high voltage to low voltage. Current will flow from high voltage to low voltage. Now, current are two types. One is DC, one is AC. DC current is direct current, AC current is alternating current, but alternating current we will study later on. Right now, we will concentrate only on direct current. So this current that is established because of difference in voltage between 2 points, is there any relationship between current and these voltages? Yes, there is. The relationship is that current is equal to difference of the potential between 2 points divided by the resistance of the conductor. I is the current on account of potential difference created across 2 points, and R is the resistance of the conductor, meaning thereby R is the resistance of this conductor. So if we just draw it again, you have a conductor with resistance R with a potential difference of delta V between 2 points. Then the current is delta V over R. This is our famous Ohm's law. Okay. Now, if you take a battery and connect any resistance to it, let us say the battery is of EMF E and the resistance is R. Is it possible that the current you get, current should be equal to potential difference over R? Yeah, but you don't get this much value, you get a value smaller than this. And why is it? It is because this battery itself has some resistance, which is called internal resistance. So if we take a battery like this is our battery. If E is the EMF and this is resistance R, we don't see this resistance since this resistance is very low. Nevertheless, it is there. So instead of our current being this much, what we get is, we get our current is equal to EMF divided by R plus R. I is the current in the circuit. E is the EMF of this battery. R is its internal resistance, and capital R is any external resistance. So this is the current, net current, which accounts for internal resistance as well. If we take a conductor of length L and whose cross section is A, then the resistance is defined as rho L by A. What is R? R is the resistance of this conductor, L is the length of this conductor. A, we can say A is the area of cross section of this conductor, and rho is resistivity of the conductor. L is the length of the conductor, and A is the area of conductor. So this is the resistance of conductor. Now, this resistance of conductor, or this resistivity of conductor rho, does it remain constant? No, it changes with temperature. How does it change with temperature? The temperature dependence is given by this relationship. Resistivity of the conductor at any time, any temperature T, is given as resistivity of the conductor at any temperature T0, 1 plus alpha T minus T0. This is the resistivity at any temperature T. This is the resistivity at any temperature T0. This is the coefficient of resistivity. It's the temperature coefficient of resistivity. So if you know the resistivity at one temperature, you can find the resistivity at another temperature, given that alpha is known to you. Now, if a current is flowing through a resistor, you will notice that this resistance becomes hot. Why does it become hot? Because the current that is flowing through it, this current energy gets converted to heat energy. And how is that? What is the relationship? The relationship is that power consumed by a resistor is given as I into V, or I square R, where I is the current flowing through a resistor R. The power consumed by the resistor is given by IV, or same thing as I square R. And that is the basic principle of you have your filament lamps. What happens is, this is very high, very low resistance. This resistance, and you apply some voltage across it. If you apply a voltage across it, what will be the power? Power will be I square R. If we convert it into voltage and resistance, what it will be? The same thing as IV, and I is same as V by R. So it is also is equal to V square by R. Now, if you want the power to be high for a fixed voltage, what will be the value of R? The value of R has to be low. The lower the value of R, higher will be the power consumption for a given voltage. Now let's see some configurations of conductors, resistors in series and parallel. If you connect some resistors like this, R1, R2, R3, then the resultant resistance will be summation of all the resistances in series. This is when resistances are connected in series. Now you have another case where you have R1, R2, R3, supplied to a common battery. In this case, the resultant resistance is given by inverse of the resultant resistor resistance is given by R1 this is the inverse of the resultant resistors. Inverse of the resultant resistor is given as summation of inverse of each of these resistances. Okay. Now next is Kirchhoff's law. What is Kirchhoff's law? It says that, let us say you have a network of resistors, component in the battery connected. Then what will happen? Suppose this is point A, B, C, D, E, F. If you start from one point and come back to the same point by any route, the total potential difference will be zero. For example, let's go across this. We start from here, then we have V, A to B, then V, B to C, then we go this way. Then there is no potential difference, and then there is EMF. Now, if we add all these things, this will be, if we take this as loss, this will be equal to, or we can say we start from here, there's a drop, this difference, then this difference. If we add all these differences, we come back to point A. And the net difference of in voltage will be zero. Now it is not necessary that we have to, this is true for only one path. No, it is true for all the paths. For example, if you travel from here to here, here via this route or via some other route, let us say this route. If we add the voltage drops across each leg, then total voltage drop across each leg, if you sum it up, will be zero. Another way of saying it is like this. If there is any current going to a point, here it is I, here it is I. Now here it gets branched. This is I1 and it gets branched into I1 and I2. If it gets branched into I1 and I2, let's talk about this junction. What happens at this junction? I incoming current is I, outgoing current is I1 plus I2. Kirchhoff's law says that current coming into sum of coming into a junction is equal to sum of going out of that junction. So if I is the incoming current and I2 and if I is the incoming current, I1 plus I2 is the outgoing current, then by Kirchhoff law, I should be equal to I1 plus I2. This. And this will hold for any node, for any situation. And this property will make this follows this phenomena, or this follows this phenomena is one and the same thing. Next is Wheatstone bridge. What is a Wheatstone bridge? You take 4 resistors, connect to a battery, RA, RB, RC, RD. Now what you do is, between these 2 junctions, you attach a galvanometer. If the galvanometer reading becomes 0, then we call it as balanced bridge. When this bridge is balanced, there is a special condition. And this special condition is that ratio of RA by RD is equal to ratio of RB RC. This is a very important condition. Now, through the Wheatstone bridge, you can measure very small resistances accurately, because you're just taking the ratios. Now, when this bridge is balanced, then it doesn't matter what is the EMF of this battery. It doesn't matter, because everything is in a ratio. It is not in an absolute term. So whether the voltage is high or low doesn't matter. In a balanced case, this relationship will still hold. Next is potentiometer. Potentiometer is a long wire of uniform resistance per unit length. Its resistance per unit length is constant. And then what you do is you attach a battery to it of any EMF, let us say. Now, when you attach a battery to this resistance, what will happen? The total EMF of this will now drop down onto this wire, right? This point will attain the highest EMF voltage. This point will be highest voltage. This point will be lowest voltage, and its gradient will be uniform. Now, this property we can use to compare EMF of two sources. How? Let us say we have one EMF source, and what we do is take a rheostat, take a galvanometer, and let us say this is EMF E1. Now what we do is we take this galvanometer, and with this galvanometer we attach a jockey. A jockey is normally this kind of solid piece of metal. Then you attach galvanometer to it as shown here, and then you try to search on this line, on this wire, you try to search where the galvanometer stops showing deflection. Now let us say at L1, distance, this galvanometer shows zero deflection, which means that the potential due to this battery and the potential drop up to this length is same, which means we can say, if we say this is the EMF per unit length, then for L1 length, what is the potential difference on account of this? Will be this one. Okay. Now what we do is, instead of E1, we now replace with E2 and try to find this battery. We replace with another battery, and then again we try to find the null point. Null point means balance point where the galvanometer doesn't show any reading. So E2 will be some another length too. Now it is very easy for us. We immediately know EMF 1 over EMF 2 is proportional to the null points. This is how you can compare EMF of two batteries. Now, why do we call it EMF and not voltage? Is because we have already seen that EMF is not equal to terminal voltage. Because of internal resistance of battery. Now, does it mean that during this experimentation, our internal resistance has gone? No, it has not gone. Internal resistance will come into play only if there is a current flowing through it. If there is no current flow through it, for example, you take a voltage source V1 and you take a resistance R And if there is no current flowing in this resistance, then it doesn't, irrespective of whether there is a resistance, whatever the value of the resistance, voltage here will again be V1 because there is no current flowing through it. So when there is no current flowing through it, the internal resistance of the battery doesn't come into picture. And in this case, epsilon becomes our terminal voltage. Right? So it's a simple way of comparing EMF of two batteries. Now, next issue is with similar technique, can we find out the internal resistance of the battery itself? Yes, we can. How do we do it? Now, in this case, what we do is we have our potentiometer wire AC our potentiometer wire. This is our any battery with EMF. It doesn't matter what value it is. Then this is the battery of our interest, of which we want to find the internal resistance. Let us say this battery has an internal resistance small r. Then what we do is parallel to the battery. Now this dotted box is a complete battery, wherein E2 is the EMF of this battery and R is the internal resistance of this battery. Now what we do is we attach a resistance R external to it, which is parallel to the battery with a switch. Now what we do is we first keep the switch open and then we find the balance point. So let us say L1 is the balance point without R in the circuit. And to remove R from the circuit, we simply open the key. Now, next thing what we do is we close this key and then again try to find a balance point on this. Let us say we get second balance point as L2, which is balance point with R in parallel to the battery. Now, what is the purpose of putting an external resistance? The purpose of external resistance is that when we find a null point here, the current through, although the potential difference across this battery means the terminals of the battery may be balanced, but which is not same as this because there is some current flowing in this circuit. And since there is a current flowing in this circuit, R is getting affected. R is playing its role. And that is what we want to do. We want to find the active role of R, means find the value of R. So value of R can only be found if there is a current flow through R. So by putting an external resistance parallel, we are ensuring that some current flows across the battery or across the small R. Now, when we get these two L1 and L2, then our internal resistance is simply R into L1 by L2 minus 1. It's simple to drive. I'm not going into derivation part of it because if it's a simple, if you do a simple Kirchhoff law application, we'll get this straight away. What is a galvanometer? Galvanometer is a very simple device. It is a moving coil inside which has some resistance. And the moment some current is passed through it, there is a pointer attached to it, it starts deflecting. And deflection is proportional to input current. Now, if our aim is just to see whether there is any deflection or not, like when we were trying to do a balancing, trying to find a null point, we are not interested in knowing by how much degree it has deflected. All we need to know is that in this galvanometer, there should be no reading. So long as there is no reading, we are okay. Now, we are not bothered much about the galvanometer. All right. But can this galvanometer be used for some other purpose? Oh, yes. Can we use it as a voltmeter or ammeter? Yes, we can. Let's see how. What is an ammeter? Ammeter is a device which measures current. Okay. Now we know in galvanometer, the amount of current that is allowed is very, very low. If we pass heavy current, the coil will burn away. So how to use it, a current which is substantial, at the same time, we don't burn the galvanometer coil? Simple. What we do is, this is our galvanometer. This is galvanometer resistance. We attach a very low resistance parallel to it. Now what will happen? The moment some current is put into the galvanometer, it gets divided in the inverse ratio of their resistances. If suppose this is resistance of galvanometer and this is external resistance, if the external resistance is very low, most of the current will get divided into, will go in this branch, and very low current will go. Just make a better diagram. So this is our galvanometer resistance. This is our external resistance in parallel. Now, if there is any current I which is fed into galvanometer, what will happen? It will get divided, and it will get divided in the inverse ratio of the resistances. If this resistance is low, more current will come here and very less current will go here. But IG and IR will have a relationship between them. So if we know IG, we can find IR, and together we can find what is the total current. Okay. So for this configuration, we can say that I is equal to IG resistance of shunt plus resistance of galvanometer divided by what it means is this I is the total current that is going in, which we want to measure. It is equal to IG, the current that goes through this branch I is the current going through the galvanometer coil, RS is the shunt resistance, and Rg is the galvanometer coil resistance. So I is equal to total current is equal to current through galvanometer, resistance of shunt, resistance of galvanometer divided by resistance of shunt. Now we know there's a limitation of Ig. We cannot exceed galvanometer are meant for very low current application. So if we say, if we maximize this, then the current measure will be maximum. If we measure current more than Imax, then the current through galvanometer will cross Imax and it will burn away. So this is how you can find out if everything is given, only one variable is unknown to you, you can find out. For example, you have been given Imax, that the galvanometer should be suitable for measuring certain amount of current. Then you have been given Rg, and you are asked to find what shunt resistance should be used, given that galvanometer can withstand only up to this much of current. So through this relationship, you can find out resistance of the shunt. Or if Rg and Rs is given, then you can find out what is the maximum current that this galvanometer can be converted to measure. Okay. Similarly, what's a voltmeter? A voltmeter is basically an instrument to find potential difference between 2 points. That's all. Now, while doing so, we must ensure that voltmeter does not draw substantial current so as to upset the basic circuit. What does it mean? That if we are trying to measure voltage between 2 points and the voltmeter itself draws some current out of it because there is a potential difference, any device, the current will flow through it. Now, if there is substantial current flow through it, our basic current in the basic test circuit will get disturbed. So how can we avoid it? That we measure the voltage, as well as for measuring voltage, current will have to flow. We know that, okay, we agree with that. But at the same time, we don't want to upset the basic test circuit. So what do we do? What do we do? What we can do is we can only minimize this current. And how do we minimize this current? We can minimize this current by putting a very high resistance, which is that if this is our galvanometer, we know it has a resistance R0. Then these are the 2 points A and B, across which we want to measure the voltage. What we do is we attach a very high resistance in series. Now what will happen? We know current will be, this is the current, this is the current. This current will be drawn out of the test circuit. Okay, this will be equal to difference in voltage between these two. Current current through galvanometer is given by the voltage voltage difference that we are trying to measure divided by total resistance. Total resistance will be Rg plus Rg plus R. Now, if we make this R very high, then obviously this will become low, and then it will serve our purpose. Okay. So this is the relationship. And if you want to find out what is the maximum voltage we can measure, the maximum voltage that we can measure across these 2 points is maximum current flowing through galvanometer multiplied by this resistance plus the external resistance. So if we want to increase this value, we simply increase this R, and we can increase the range of our galvanometer for measuring voltage. We've already studied capacitors in our last lectures. And we have used capacitors just like an object which is coming in the circuit. Today we will see the mechanism of its charging in an RC circuit. This is our capacitor. What we do is we put a resistance R in series, and we take an EMF source to charge it. There will be if we set up a circuit like this is the EMF, this is the resistance in the circuit, this is the capacitance, and if there is there will be a current established in this circuit, and we know the by C is the voltage drop Q by C, because we know our capacitance is Q by V, or V is equal to Q by C. So voltage across capacitor is this much, plus another drop because of resistance this much is equal to the voltage supplied by the battery. Okay. Now we know that R if we convert R into dq by dt, this is the equation we will get. And this differential equation, if we solve, what we will get is this this Q is the Q at any time t. Q is equal to charge on capacitor at any time t. Okay. So this is the basic differential equation. If we solve this differential equation, what we will get is, we will get Q as EC which says Q acquired during charging from t's time 0. If the charging starts with no charge at time t0, then at any time t, the charge accumulated in the capacitor is given by this relationship, wherein this is the EMF of the battery, to which this capacitor is attached. C is the capacitor value, capacitance of this capacitor. T is the time, at any time t. I mean, if you can write like this, Q at any time t, which is the same thing as this t, and this is the R. R is the external resistor in RC circuit. This R is this R, and C is again the capacitance. Then charge at any time t is given by this relationship. And if you see graphically, what will happen is, if we plot t versus Q, it rises rapidly, and because of exponential function, this is the maximum. Now, what is the maximum voltage that a capacitor can acquire in an RC circuit? When it gets fully charged, the current flow stops because there is nothing more to be charged. Now, if current flow is 0, then all of this voltage will appear across this capacitor, right? So, if we use this formula, or Q is equal to CV, if we say full charge, this will be equal to what? C time epsilon. Because this capacitor cannot acquire more charge than E times epsilon, because this voltage cannot be more than this voltage. So this is the maximum charge which can go in, and which is, after a while, it becomes asymptotic. Now, time t, which is equal to RC, sometimes this is also called tau. We write 1 minus E. Okay, forget. Let's not confuse it. T is, when T is RC, this is T, this T is called time constant. And if we take T, this time constant is also called tau. At tau, the charging is about 63%. of total charge. So it's a very rough measure as to if we give charging time equal to a tau time, you know that about slightly more than 60, the capacitor will be charged slightly more than 60%. It has no other significance more than that. Now we have seen the relationship of charge on a capacitor vis-a-vis time during charging. Now what happens if we discharge a capacitor? Okay, we have a capacitor. Again, we attach a resistance and we simply short it through R. Current will be established. Okay, then this current, the drop across this resistors will be totally on account of drop across this resistance will be totally on account of the voltage that the capacitor is carrying at that time. So this is the voltage drop across this resistance, and it is purely on account of voltage the capacitor has, and we know C is equal to Q by V. V will be equal to Q by C. This is our basic relationship, which can be also written as QC is equal to, this is our differential equation. And if we solve this differential equation, what we'll get is Q at charge on the capacitor at any time t is given as total charge that it started with. This is the initial total charge and this is the external resistor in RC circuit. This T is same, and for convenience we can also say, like, if we have charged this capacitor in this configuration, then the full charge would have been C times E. So we can replace Q naught by C epsilon naught. This is only if we knew that the charging was fully done through an external voltage source of this value. Otherwise, we have to know what is the initial charge irrespective of how it was charged.